Hello everyone, here we are again in our next video. This time we're going to be talking about energy analysis of cycles. So first thing we're going to talk about is a thermodynamic cycle. And what is a thermodynamic cycle, you may ask? Well, a thermodynamic cycle is basically going to be a sequence of processes that begins and ends at the same state. Now, putting that in simpler terms, basically your properties are going to start and end at the same place. Okay, so whatever you have at state 1 for pressure, at the end of this cycle you're going to go back to that pressure. Same thing with volume, temperature, whatever else you got. Okay, you're going to start and end at the same place. Now, with that, let's write some equations. So our delta E, so our total energy, the change in that for this cycle, is going to be Q of the cycle, so our heat transferred in, minus the work for the cycle. All right, so we got our energy transferred from heat and then the energy from work. Now, if you think about it, we're starting and ending at the same place, right? So if we're starting and ending at the same place, this term here, this change in energy, has got to equal 0. Okay? So just think about what you have for that energy balance part of your equation. You're starting and ending at that same location, so you can't have a change in energy. So this is going to be because of a return to the initial state. Okay. Now, that being said, what does that tell us about Q and W? Right. So if delta E's got to equal 0, then that means Q has to equal W. So Q cycle is going to equal the work for that cycle. Now, this is for a thermodynamic cycle. That's what we're talking about here. And thermodynamic cycle, if you hear that, it just means you start and end at the same place, and Q's got to equal W because your total change in energy has to be 0 because you're starting and ending at the same place. Okay, so that's what that one is. Now, the next one we're going to talk about is a power cycle. And if you take a Thermo 2 class, for example, one that would come after this one, you'll learn a lot more about the power cycle. Basically what this kind of cycle does is it's going to deliver a net transfer of energy by work. Okay, and for this one let's draw a picture, make it easier to explain what's going on. So let's draw this little box here. This is going to be our system. So whatever we got going on in this system, and then we're going to have a hot body here, and then we've got some cold body down here. Okay. Now what's going to happen is we've got a temperature difference between these bodies and our system. So this hot body, there's a temperature difference. Remember, we always go from hot to cold. So we're going to have a Qn that's brought about by that hot body. Okay. And the system then is going to take this energy and it's going to have work. So it's going to produce work. And work that's generated is going to be equal to Qn minus Q out. Now what is Q out, you may wonder? Q out is going to be the energy transferred from the system to the cold body. Okay, due to a temperature difference. So we've got a Q in from the hot body, Q out from the cold body. Work of that cycle is the difference between those two. Okay, so for a power cycle, the work that we get is going to be Q in minus Q out. Okay, so that's only for a power cycle there. Now let's write down what all these terms are. So work of the cycle, that's going to be the net energy transfer of work. basically we're saying W is going to be greater than 0. Now if W is greater than 0, you're transferring energy out of the system essentially. So you could use that energy to do something else. So you could use it, you could use it to turn a shaft, something like that. Use it to power something else. That's how I think of it. Okay, so we're generating this net energy transfer of work using this kind of cycle. Qn is going to be the heat energy transfer to the system. And that's going to come from a hot body. And then Q out is going to be the heat energy transfer out of the system. All right. Now Q in is going to be greater than Q out, right? So that's what we'll always have. Now engines operate on power cycles. So if you take a more advanced thermodynamics class, you will learn all about engines, how they operate, what components you have to create these power cycles. Okay. Now we have to have a way to rate the efficiency of these cycles. And this is going to be the thermal efficiency. So the thermal efficiency is just going to describe the performance of a system that's undergoing a power cycle. Essentially, it's just basically gives you an idea of how much energy added by heat is converted to your net work output. So if you're taking this heat energy in here with Qn, how much of that are you able to turn into a usable network output? Okay, so all of this Q out, that's kind of like wasted energy if you think about it. If you can take all of that, Q in, transfer it all to work, you'd be doing great. Okay, they haven't quite figured out how to make that happen yet. Now, what we need is some equations. So for thermal efficiency, we're going to have the variable, it's going to be eta. So that's kind of that fancy looking N symbol. And eta is going to be the work of the cycle over Qn. So it's just a ratio of how much work you're generating over the energy you're bringing in from the heat, from that hot body. Another way of writing that, since work of the cycle is Qn minus Q out, we could say that eta is Qn minus Q out over Qn, which, if you notice, you got Qn over Qn. So you could make that equal 1 minus Q out over Qn. So this is going to be thermal efficiency. You will not find an efficiency equal to 1. That would be perfect case, perfect scenario. That would mean the work that's transferring out is the same as the energy that's transferring in from the heat. You will not find that. That would be a perfect system, so you're not going to have a value of 1. The closer you get to 1, the better off you are. Okay? So let's put on here, eta is going to be less than 1 because not all added heat energy can be transferred or converted to work. Okay, so you should always get an eta less than 1. So that's a power cycle. Again, we use it to have a net energy transfer of work. So then we could use that work and do something else with it. Okay, next page, what we're going to have will be refrigeration and heat pump cycles. These might be easier for you to imagine because you've obviously seen a refrigerator probably. So let's consider that example. So we've got a refrigerator in the kitchen at the house. Now what happens with that refrigerator is we've got heat that's moved from the inside of the refrigerator, which that's going to be a heat source. That heat's going to be moved to the warmer air outside in the surroundings, which will just be the kitchen atmosphere basically. Okay, so we're moving heat from inside the refrigerator to outside the refrigerator. Now, obviously, you have to have something happening to make that work. Okay, so work is going to be required to make that happen. Now, let's draw a picture here for this. Let's put it over here. So here is our hot body. Let's put a little box for the system. And then here is the cold body. Okay, so now we've got that. Now for this one, the hot body, this is going to be the surroundings of the refrigerator. This cold body is going to be inside the refrigerator. And then the system will be all those components that make the refrigerator actually work. So now what's going to happen is we're going to remove heat from the inside of that refrigerator using the components in our system, and that's going to give us this QN. So we've got energy being transferred to the system from that heat, and what's going to be going on here is that we've got work being done on the system. So there's some external work being done. So a refrigerator is obviously plugged in. That electrical power supply is going to make your system make all of these things happen. Okay. So work, we have the arrow drawn into the system because work's being done on the system, and that's going to equal Q out minus Q in. Right, now we already know what Q in is. Well, what's Q out? Q out is going to be the energy that's transferred out of the system to the surroundings. Like that. Okay. In this instance, we're going to have a Q out greater than a Q in. Okay, so it's kind of opposite from what we had before. Now let's write out what all of these terms are. So W cycle, that's our net energy transfer by work. Now in this case, it's opposite of that power cycle. Power cycle, we were sending energy out. Here, bringing it in. Okay. Qn is going to be the energy transferred by heat into the system. And then Q out, obviously going to be energy transferred out. So now we've got that. Okay. So that's kind of how the refrigeration cycle works. All right, we got Qn from the cold body this time, whereas the power cycle, it was reversed. Qn was from a hot body, the warmer body. Now with a heat pump is kind of like the refrigeration cycle. They're a little similar. Let's draw a picture for this one. So here we've got our hot body, and we've got a system, and then we've got a cold body down here. So in this instance, if you think about a heat pump that you would have on a house for part of your HVAC system, the hot body is going to be the interior of the house. The cold body would be the surroundings, so outside of the house. Now in this one, we're also going to have work being done on the system. So the arrow is going to point this way. So we've got work for this cycle. This one's going to be Q out minus Q in, just like we had with the refrigeration cycle. But in this case, our Q in is going to, so this one, what we're trying to do, let's see, is we want to kind of do the opposite thing. So with the refrigerator, you were trying to remove heat to keep things cold. With a heat pump, what you're trying to do is you're trying to warm something up. So we're still going to have Q in from our cold body. So it's going to take heat from the surroundings and it's going to put those into the system. Work's going to be done on the system, and that works Q out minus Q in. And then what happens is through this work, we're going to be able to transfer energy from heat into the hot body, which in this case, think of that being the interior of a house. So this Q out can be used to warm the interior of the house. Okay. So the difference between the refrigeration cycle and the heat pump cycle is basically kind of what the hot body is, what the cold body is. All right. So they've switched, if you notice. Before, in the refrigeration cycle, the hot body was the surroundings. Now the cold body is the surrounding. All right, so that's kind of the difference there. They serve different purposes. One's to cool things off. Other one is to heat up the inside of a house, for example. All right, so let's write some notes here. So with refrigeration, we want to cool or maintain a temperature in a space with lower temps than the surroundings. Okay, now that's refrigeration. Now with heat pumps, we're kind of concerned with the Q out, right? So with the refrigeration, we want to get heat out of the inside of the refrigerator, so we care more about Q in. Now with the heat pump, we care more about the Q out because we want to warm up that hot body. We want to warm up the interior of the house. So let's put we're more concerned with Q out. Right? Now, with that being said, we're going to have coefficients of performance. And this will tell us basically how our efficiency is. All right, so our coefficient of performance, we're going to have two of them. For refrigeration, our symbol will be beta, and beta is going to be Qn over the work of the cycle. And we could rewrite that to be Qn over Q out minus Qn. Okay, so that's what you'll have for refrigeration. And we'll have a coefficient of performance for heat pumps also. And that symbol will be gamma. So gamma, since we're concerned with Q out, we're going to have Q out over the work of the cycle. So that'll be Q out over Q out minus Q in. Just like that. Okay? So closer to 1 you get, the better off you are. It's not going to be equal to 1 because that would be a perfect ideal case, which we don't have. There is no heat pump out there that's 100% efficient. So, but that's how you can measure your performance for refrigeration and a heat pump cycle. Okay? All right, guys, let's stop there and we'll pick it up in the next video.